Hi, I'm Dr. Robin, aka Double O Pi. This video is the first of what will probably be a 5-video series on metal-ligand complexes. In this video, I'm going to talk a bit about how and why these complexes form. I want to start by saying that metal-ligand complexes are weird. On the one hand, they don't quite follow the rules that you may have learned about valence bonding when you learned about covalent bonds. On the other hand, even though they kind of sound like they might be ionic compounds when you first start talking about them, they aren't ionic in nature either. In short, they're complex things. And as far as I can tell in my reading, that is how they got their name. So let's start by talking about a few principles about ionic and covalent bond formation in the hopes that it will help you understand what metal-ligand complexes are and aren't. Let's start by reviewing what you probably know about ionic compounds. Specifically, why and how do they form? And why do they dissociate in water? In Gen Chem, you probably learned that ionic compounds formed when positively charged ions, or cations, react with negatively charged ions, or anions. Why do they do this? You probably learned that this is nature's way of neutralizing a charge. So, for example, sodium with a +1 charge and chloride with a -1 charge come together to form sodium chloride, which has a net charge of 0. In the case of cobalt-2 hydroxide, cobalt has a +2 charge and hydroxide has a -1 charge. If you just had one cobalt ion and one hydroxide, that would give you an overall charge of -1. In order to make an ionic compound with a neutral charge, you'd need 2 hydroxide ions for every cobalt atom. We know that some ionic compounds dissociate in aqueous solution. In other words, the ions come apart. But I just said that ionic compounds form because charges need to be neutralized, so why does this happen? The key to understanding this lies in your knowledge of intermolecular forces. Water is a polar molecule with a positively charged end and a negatively charged end. Although these charges are much, much smaller than the charge on an ion, having several water molecules around each ion can also neutralize the charge. Notice that the water molecules rotate so that the negative ends face the positively charged sodium ions, while the positively charged ends face the negatively charged chloride ions. Here's something that you might not have thought about with regard to ionic compounds. Solid ionic compounds will have a nice, orderly crystal structure, whereas those same ions, when solvated by water molecules, are highly disordered. In other words, the dissolution of an ionic compound is entropically favorable. That's one of the reasons it happens. Now I want you to think about the reverse process of dissolving, that of precipitation. Specifically, what is the mechanism by which that happens? At first you might think that this is relatively straightforward. All we need is for the ions to come back together again, right? But you have to remember this is happening in solution, so it isn't quite so simple for the ions to join up. This can only happen if some of the solvating water molecules move out of the way. Now let's think about the formation of cobalt-2 hydroxide. For simplicity's sake, I'm going to leave out the solvating water molecules, but please don't forget that they're there. If you were to just look at the overall written reaction, you might say it looks something like this. You have your cobalt +2 cation and 2 hydroxide anions, and they come together like this. But that's actually not right. If you think back to your study of reaction mechanisms, you might recall something called collision theory. Basically, a reaction occurs when 2 molecules collide at the correct angle and with enough energy. A corollary to this is that you can't ever have more than 2 reagents connecting at once because the laws of probability tell us that it's unlikely for more than 2 molecules to collide at the right angle and with the right energy. So if you have a reaction with more than 2 components, they need to come together in a stepwise fashion. First, 2 will come together, then that product can combine with a third thing, etc. So how might cobalt hydroxide actually form then? Well, you'd have to do it in 2 steps. First, one of the hydroxides would have to connect with the cobalt-2+ ion to form this weird ion that has an overall +1 charge. Then another hydroxide can react to form the ionic compound that we were expecting. I want to go back to this cobalt ion with a single attached hydroxide. When I teach this concept in person, I ask my students what name they might call this thing, and most often they'll call it an intermediate or a transition state. Both of these terms refer to a molecule that only exists briefly. It's there, but only until the rest of the reaction happens. Sometimes an intermediate only exists for such a small amount of time that we can't even detect its presence. And if you were trying to precipitate cobalt-2 hydroxide out of solution, you would absolutely get ionic intermediates like this forming. But if you were to make a solution of cobalt 2 ions and hydroxide, you would also find a lot of cobalt hydroxide +1 compounds floating around in solution. These are compounds that aren't temporary. They aren't a transition state. They are stable. And they aren't held together by an ionic bond. I like introducing metal-ligand complexes by talking about ionic compounds because almost everyone who understands reaction mechanisms can see that a molecule with one cobalt 2 ion and one hydroxide must form in solution. You can even understand why this particular complex might be stable in water because it's an ion with a +1 charge, and therefore it can be solvated by water molecules, just like any other ion with a +1 charge. But that is as far as this analogy goes. Because when you make a solution of cobalt 2 and hydroxide ions, you don't just find this molecule floating around in solution. You also find a cobalt with 2 hydroxides, not a precipitate, but an actual solvated molecule. You find a negatively charged complex of cobalt with 3 hydroxides. You even find a cobalt complex with 4 hydroxide molecules. Clearly, this is not just about neutralizing charge. What is going on here? The last clue towards understanding metal-ligand complexation comes from your knowledge of Lewis acids and bases. You might remember that a Lewis acid is defined as an electron pair acceptor, and a Lewis base is defined as an electron pair donor. The classic example of Lewis acids and bases are ammonia and H+. Ammonia is NH3, which we can write this way, plus it has a non-bonding pair of electrons. It is this pair of electrons that make ammonia an excellent electron donor or Lewis base. A neutral hydrogen has 1 electron. H+ therefore has no electrons. It's just a lone proton. Because its valence shell is empty, it can accept the electrons that ammonia is willing to donate. It is a Lewis acid. When hydrogen accepts the electrons that ammonia donates, a covalent bond is formed, creating the ammonium ion. But remember that even though the bond being formed is covalent, it can break. In other words, the ammonium ion can deprotonate, turning back into H+ and ammonia. This reaction can run both ways, so we need to think of it in terms of equilibrium. The same thing happens when a cobalt hydroxide complex forms. You might think that these 2 ions come together because they're ions with opposite charges and opposites attract. But remember that metal-ligand complexes are covalently bound. So let's consider how this might happen. The electron configuration for cobalt looks like this. When you oxidize it to cobalt 2+, you would remove both of the 4s electrons because those are in the valence shell. Normally I would just write that as argon 3d7, but I want you to notice that the valence shell 4s is now empty. In other words, this has space to serve as an electron acceptor. Cobalt 2+ is a Lewis acid. And if you look at the structure of the hydroxide ion, you can see that it has 3 non-bonding pairs of electrons, making it a good Lewis base. So when a complex forms, a covalent bond is formed between the Lewis acid, the cobalt, and the Lewis base, which is the hydroxide. One thing that you should definitely remember about the cobalt and hydroxide being Lewis acid and base is that they really behave the same way that our ammonia and proton did. The hydroxide can leave the cobalt or come back to it. And whether they're bonded or not will depend a lot on equilibrium conditions. We'll talk a bit about that in the next video and in more detail in subsequent videos in this series. Let's wrap up this video by discussing some terms that are used in discussing metal-ligand complexes. First of all, let's just say that a complex includes a metal serving as a Lewis acid with 1 or more Lewis bases bonded to it. Throughout the series, the term complex is generally what I'm going to use to refer to one of these molecules, but there are some other synonyms that get used. I also use the term metal-ligand complex. I've also seen these things called complex ions. That's a term that I don't really like because they aren't ionically bound, and as you'll see in the next video, they also don't necessarily have a charge. Finally, you will sometimes see these referred to as adducts. In one sense, that's a good term because an adduct is something that's formed in a reaction between a Lewis acid and a Lewis base. But not all adducts are metal-ligand complexes, so I will also not be using this term. And the other terms I want to define both refer to the parts of a complex. Again, this complex is formed between a metal, which serves as a Lewis acid, and one or more Lewis bases. We often refer to the metal as the central atom in the complex. When we're talking about generic complexes, we use the letter M to represent our central atom. Finally, as I said earlier, the central atom bonds with one or more Lewis bases. We call these Lewis bases ligands. Now, if you're a biologist, you may be thinking, hey, that's not how I pronounce that word. I call it a ligand. And you would be right. I don't know why biologists and chemists pronounce this differently, but as chemists, we call these things ligands, so expect me to use that pronunciation in the videos that follow. Before we get into the summary, if you found this video helpful, please take a moment to click all of the things to engage with the YouTube algorithm. In this video, we've talked about how metal-ligand complexes form when a covalent bond is formed between metals and one or more Lewis bases. These complexes form from one or more ions, and the final adducts might carry a charge, but they are not ionically bonded. As I've said before, this has been the first video in what will probably be a 5-part series. Coming up in part 2, I'll answer some commonly asked questions about complexes and complex formation, and I'll start talking a bit about the associated equilibrium calculations. Parts 3 and 4 will go into detail on how to calculate equilibrium concentrations of metal-ligand complexes. And then part 5 will wrap up by talking about chelators, as well as the real reason I started with ionic compounds in this video. Hey, thanks for watching. I'm looking forward to seeing you again on the channel soon. Dr. Robin, signing out.